Yeah, I guess we can start. And today again is the second lecture of our preschool. It's on a review on quantum mechanics by Shaikot, Jahan, Shuvo. And yeah, over to you, Shuvo.
All right, so thank you, Rakin. Again, welcome everyone. So, this is just a review class of some selected topics from quantum mechanics, and mostly the agenda for today's meeting is to review the basic postulates and some notations. So, review the basics. By basics, we mostly mean the postulates of quantum mechanics. We'll start with that. Then we will introduce the bracket notation and discuss some quantities that will be of interest to us when we do quantum mechanics. While doing QM. This really covers, how we define a probability, the expectation values, eigenvalues, Hermitian operators, and all that stuff. So we'll review this in the first half, and then we'll just briefly talk about the Schrodinger equation. I mean, that's the very foundation of quantum mechanics. And, the main goal is to solve the Schrodinger equation. And I'll show you guys a very brief example on, the problem everyone knows and loves. That is the problem for the infinite potential well. I won't derive them completely because that will take some time, but I'm just going to give you guys the result and maybe you can do it on your own if you're free. But then on the second half, I plan to go over the harmonic oscillator. This is the most important thing or the most important agenda for today. We want to talk in details about the harmonic oscillator, and this will play a key role in introductory quantum field theory that you guys are gonna take in a few days. Like a lot of the material translates over to QFT. So this is something we'll try to see. And lastly, if time permits, I'll just give you guys a glimpse of the Dirac equation. That is if time permits. Okay, so with that, let's start. So first things first, again, I'll not, at first I thought I should discuss some historical things, but then I realized if I start to discuss the history, it's gonna, again, since we're here on limited time basis, we'll just focus on the formalism. So we want to do quantum mechanics, and since I'm assuming everyone is familiar with classical mechanics, in classical mechanics, oops, wait, what is that now? Oh, in classical mechanics, if you know the position of a particle, let's say you are dealing with a particle, and the momentum of a particle, basically, everything there is to know about that particle. So in that sense, you can think of them as the independent variables in classical mechanics. So when you do quantum mechanics, what you do is you take these variables. So this is a variable, like a number, and you promote it to an operator. Uh, some people use hat. For this lectures, I'm not gonna be using hats. I mean, if that makes you comfortable, you can use it. But I'll just use the capital X to denote that this is an operator. And I'll explain what do I mean by an operator in a few bit. So we take the classical variable and we promote it to an operator. So this object here is known as an operator. So what do we mean by this? Well, the variable is like a number, right? If you plug in a certain value of t, you'll get some certain value of x. However, this is an operator, so it's not like a number. It's rather like it can be a differential operator. We'll see in a few bit, like this will be represented with the value of x in the eigenbasis, in the position eigenbasis. But if someone does this on the momentum basis, it will look something like this, like a differential operator. So this is the first postulate of quantum mechanics, that is, you have your dynamical variables, right? So instead of treating them as numbers, you promote them to operators. And if this explanation here seems confusing, think of them like matrices. Even a differential operator can be thought of as an infinite dimensional matrix. And if you want to read more details, my personal favorite is Shankar's book, R. Shankar, Ramamurthy Shankar, and I think the name of the book goes by Principles of Quantum Mechanics. Um, and I think he discusses everything, like how you go from finite basis to infinite basis and all that, all the details in chapter 1. So this is our first postulate. That means the dynamical variables will now be treated as operators. And when we do that, we also get some subtleties. For example, if you now take the momentum as you took the position, x, again, this is the variable, a number type of thing. Now let's say you are promoting this to an operator, capital P. What happens is, in classical mechanics, you have this x times p equals to p times x, classical mechanics. However, in QM, I'll just skip the t's from now on. This is an implicit, this is just, let's get rid of t, just for some time. In quantum mechanics, this is not true. In quantum mechanics, x and p, they do not commute. So this is something we called non-commutativity. In other words, the commutator which is defined by, let's say, for x and p, this is non-zero. Now, if you're someone who's familiar with Hamiltonian mechanics, or you know, you have seen Poisson brackets, if I recall correctly, the Poisson bracket for the variables looks something like this. I think this is a 1. Or am I missing a minus sign? I'm not sure. Maybe this thing is off by a minus sign. But this is something very similar to the commutator. This is the Poisson bracket, a Poisson bracket. This also acts like, this is very similar to the commutator itself. Like you have some derivative operations and minus the antisymmetric part. So in quantum mechanics, this commutator is really equals to I, H bar, and the identity operator. So this is a big postulate. You can try to prove it, but that will require some other tools that we're going to discuss in a few bit. And by the identity operation, I mean it can be the identity matrix if you're working in finite dimensions, and it can be a delta, like a delta function if you're working in infinite dimensions. And I'll briefly talk about them as well, but for now, keep this in mind. So this is where quantum mechanics differs from classical mechanics, like X and P, they don't commute. So there is non-commutativity. That's what makes it non-trivial. So this is the first thing that I wanted to talk about among the postulates. Then the second thing would be to introduce a few notations. So let's talk about them. So let's introduce the bracket notation. We can even do quantum mechanics without bracket notation, but since you're doing QFT, I guess this will be a nice addition. So think of this, let's say this is a column vector. Again, I'm not going to give you the full rigorous definitions because I think that will be too much. I'm assuming there are people who have never seen bracket notations or people who are not familiar with linear vector spaces and all that. So I'll try to give the whole discussion as mild as possible. So let's say you have a column vector like this. Instead of writing it just psi, we're gonna call it a get psi. So this arrow type of thingy is known as a ket. And let's say you have a 5, which is a row vector. This will be written like this. And this symbol will be known as a bra. This is the essence of the bracket notation. And if you are someone who already knows about linear algebra, what happens is that we call these kets as vectors in an abstract space called Hilbert space when we were doing quantum mechanics. And these bras are actually the vectors that live in the dual space. And yeah, that's essentially the definition. But if you don't know about vector space and dual vector space, that's okay because again, we are not we're not going to be that formal. So for our discussion for now, when we talk about finite basis, this is fine. This is pretty okay, column vector, row vectors and stuff. So now what you can do, once you have a row vector and a column vector, you can do a dot product type of thing. That's something we will call in quantum mechanics as inner product. So inner product is just a um, generalized dot product. You can think of it like that for now. So the inner product is denoted by this. Let's say you want an inner product of psi and phi. It looks something like this. So what this means, this really means, you are just doing this with this. So that means you take the column vector psi, then turn it into a bra. That means you transpose it, turning the column into a row. Similarly, if you want to compute the ket of phi, you take the row and turn it into a column. And how do you do that? You do that with the transpose thingy. Assuming all these elements are real. If they're complex, you have to do a Hermitian conjugate, and I'll talk about that as well in a few minutes. So for now, just know that whenever you write something like this, you are essentially referring to a number that comes out of the inner product. So these are two notational stuff that I wanted to introduce. Now, in terms of quantum mechanics, we said we have to promote our variables, the dynamical variables to operators. So what sort of operators are we interested in? Uh, we are only interested in, okay, I shouldn't say only, we are mostly interested in Hermitian operators. So what are Hermitian operators? Well, let's say you have a matrix. For example, think of a matrix. Let's say there's a matrix A, but the elements of A can belong to the complex number field. So if you do a Hermitian conjugate that is denoted by a dagger, this symbol is called a dagger. This really means you take the complex conjugate and transpose it, which is the same thing as transposing it first and taking the complex conjugate of all the elements. So an Hermitian operator is something that satisfies A dagger equals to A. This is the definition of an Hermitian operator. So this is the definition. And then I'm going to introduce another term called eigenvalue and eigenvector. So I think eigen is a German word, if I'm not making any mistake, and which really means proper. So what happens is that let's say you have a column vector or a column matrix like this, and the operator, let's say A, which can be thought of as a big matrix, with elements. And it acts on the column and gives you another column with some different entries and stuff. This is the most general case. So now let's think of this big matrix as A, this column vector as psi, and this column vector as some new vector phi. So we can write this as this, right? However, in case phi becomes some lambda of psi, where lambda is a scalar. It can be a complex number, and that's okay. So in case we have something like this is a number. If phi happens to satisfy this condition, then you can write this equation as lambda psi. So what's really happening is that if you have a vector like this, you do some sort of a transformation, you are either scaling it, into something bigger, or maybe you are making it smaller. And nothing else changes. So this sort of scenario or this sort of equation is known as an eigenvalue equation. And for operator A, the lambdas are known as the eigenvalue. And this vector psi is known as the eigenvector. And in quantum mechanics, we'll be essentially solving eigenvalue problems. That's all that is. Now, since we said we are mostly interested in Hermitian operators, and we defined Hermitian operator like A dagger equals to A, this will lead to the conclusion that if H is a Hermitian operator, the eigenvalues will be real. H is real. In fact, this is something that you should do as an exercise. And I'll give you the tools to do it as well as we you know, continue through the lecture. So, okay, now that I discussed, okay, so I'll just zoom out a bit just to see. Okay, so I discussed all of this. I discussed inner product. I discussed what an operator is, the eigenvalue and eigenvectors. I also talked about commutators, right? Okay, so now, okay, I think, yeah, I should go to the Schrodinger equation and then as, invite people to ask questions. All right, so again, this is oversimplifying it, when I'm saying essentially today, we are just going to try to solve eigenvalue problem. That's it. So with that in mind, ladies and gentlemen, everyone, may I present the Schrodinger equation that you all know and love. Oh, and this h bar is the reduced Planck constant given by the Planck constant by 2 pi, just in case you were wondering what h bar is. So this is the equation that governs everything. And let me now explain bit by bit of this equation. So this h over here is a Hermitian operator known as the Hamiltonian, the energy thing from classical mechanics. This psi is called a wave vector. So why we're calling this a wave vector? Well, this is some vector which is in an abstract space. It might be finite dimensional. For example, if you're doing a spin half system, like electrons, you are solving things for electrons and stuff. And it can be infinite dimensional too. For example, the infinite potential well or the harmonic oscillator, as you guys will see later on. And here, I can try to justify a little bit why this is the equation, because if you do classical mechanics, there you can see Hamiltonian is the generator for time evolution. That's one way of writing this equation. But if you think deeply enough, the argument is kind of circular. It goes both ways. Like if this equation is true, then Hamiltonian becomes the generator of time evolution. And I think I should make this notation a little bit more clear. So when I'm writing this equation, what I'm really meaning is the following. H bar d dt psi of t h. And another assumption that I'm doing over here is that the Hamiltonian is time independent. For our discussion today, it's time independent. You can have time dependent Hamiltonians, that's okay, but then you will have to do perturbation theory, which is not in our agenda today. So yeah, this is the equation in its full glory. And the formal solution can be written like this. I think to write like this. Yep. You see, this Hamiltonian really governs the time evolution. So it takes some. I shouldn't draw pictures because I said size and abstract kit, but just think of it like this. This is some vector psi of, at time 0. There is something acting on it. I don't know, some guy comes in and pushes it. And maybe after some time it goes over here as well. You can think of it like that. Again, this is really not correct because you are dealing with abstract stuff, but just in case you wanted to see a picture. So as I mentioned before, I said, okay, we are going to try to solve the eigenvalue problem, but you might ask, okay, where is the eigenvalue problem here? Well, it's coming. It's coming in a bit. So this Hamiltonian here, this is again, since we're doing quantum mechanics, it's an operator. And since we are working in abstract space, so far, this kit size and the operators, they don't have any explicit representation. And by explicit representation, I mean they don't have any, let's say you cannot think of them as matrix for now. You cannot think of them as differential operators for now. If you want to do that, you have to select a particular representation, and that's where some other definition comes into play. And I'll show that now. So this psi again, it's an abstract thingy, abstract thing. So if all of you are familiar with the 2D or 3D vector mechanics. So if you had a vector like this in the xy plane, you could always project it, right? Either on x-axis or y-axis. You call it components and stuff. So we're going to essentially use this idea, is that since from classical mechanics, we want to do things with the positions and the momentums. So we now define two bases, let's say the position basis. And this is one of the vectors in the momentum basis. And we can also work with another useful thing that is known as the energy basis. So energy basis is pretty special, as you will see later on. So we can define the energy basis or the elements, the vectors inside the energy basis as follows. If you have the Hamiltonian operator and write down the, okay, should I? This is bad notation. Okay, let me just write psi of e so that you understand this is energy basis. Okay, psi of e. So let's say that you have the Hamiltonian, and if you apply it on an kit in the energy basis, that will spit out the eigenvalue as the energy eigenvalue of that particular state, and it just scales the vector. This is how people define the energy basis. And this is indeed the time-independent Schrodinger equation. This is what people call the time-independent stuff. Because if you are working on the energy basis, you get the eigenvalue equation. There is no time dependence here. And this eventually helps in solving this equation, the time-dependent one. Time-independent Schrodinger equation. And this position basis and momentum basis, well, how do they help? They help us in defining something called a wave function. So how do we define the wave function? You see, when we talk about wave vector, we use the word vector, that's an abstract thing. But when we talk about wave function, this should be something very familiar, like some f of x or f of p, right? So we define it like this through the inner product. So we take the abstract vector, we project it into the position basis. Just something you did in your vector mechanics course, or when you were doing vector mechanics. Let's say you have this vector A with some A x hat, B y hat. If you take the dot product with x, you get what? You get A. So that's like you're measuring the projection. Similarly, again, this is a two-dimensional thing, but this is an infinite dimensional thing or abstract thing. and you are taking a projection of that abstract vector. So this is your, I think the formal term is called position basis wave function. Similarly, you can go for the momentum basis wave function as well, phi of p. Does that make sense? Give me a few more minutes and then I'll be taking questions. So essentially, all of this helped. And now since we also introduced this energy basis, we can also go for the energy basis representation too. I'm running out of notation, so let's call this psi of epsilon. And this will be your energy basis wave function. You can even call it position space wave function, momentum space wave function, or energy space wave function, and so on. It's up to you. So we now have some representation for the abstract kits. A similar argument goes for the bras as well, because the relation, let's say you have some kit and the elements of this kit are in general complex numbers. The bra of this is defined through the Hermitian conjugate of this. So once you have this, you can think of it like you want to take this thing, you are finding a representation for the bra. So this is just P psi dagger psi star. Okay. And now that you have this, we have some representations for the states or state vectors. We want to find some representation for the operators. Now, again, there are justifications and you can find them. I personally like Shankar's book, Ramamurthy Shankar, but I think Griffith's is good as well, and Sakurai is also awesome. So pick whatever book you like. So to find the operator representations, I'm just going to give you guys the result. I'm not going to go into any details. But if you want, you can look into R. Shankar, Principles of Quantum Mechanics, Chapter 1, if I recall correctly. So the operator representations are the following. The X operator in position basis, I mean, they look different in different bases. So in position basis satisfies X acting on the operator acting on the position basis vector gives you the value of the position. So it satisfies an eigenvalue equation. So essentially, if you have a capital X, this translates into some small x, like this is an operator and this is a number or a variable, whatever you want to say. And the momentum operator in the position basis will look something like this, negative I h bar dd of x. Or if you're if you're working in one dimension, you can write d, and if you're working in multiple dimension, let's say in 3 dimension, you have px, py, and pz. So this will look like the partial derivatives and so on. With all these ingredients in our hands, let's try to see first what happens with the energy basis equation. Again, E is the energy eigenvalue for this particular state. So how are we gonna do it? Let's try to multiply with the position basis. Let's say we want to see how this equation looks in the position basis. Since he is a number, it can go past. This is x with psi of e. Now we have to write something for h, right? We haven't explicitly written anything. So the Hamiltonian is the kinetic energy part and the potential energy part, right? The kinetic energy is written as the momentum squared divided, and assume we're dealing with a massive particle. So this is momentum squared by twice the mass, and v is some v of x, it's just a potential. Again, this p squared v, these are operators, and mass is a scalar. So what we do, we plug this in, p squared by 2m plus v of x, oops, sorry, capital X. I mean, let's say you had, in classical mechanics, you have some 1/2 of x squared, some potential. So in quantum mechanics, you'll have the capital B of capital X as 1/2 capital X squared, something like this. So that's why I wrote a capital X, and you write this, and you can call this E and psi of E of X. Now, I'm gonna do something over here, and I'll explain what I'm doing. So you have I h bar dt of x whole squared, 1/2m psi e of x, v of small x, that means the number thingy, or the position value thingy, psi e of x, e of psi e of x. Why did I write it like this? Well, for now, think of this v of x as some function of capital X, right? So let's say you have some 1/2 of x squared e over capital X, negative sine of x, and yada, yada, yada. Whatever you do, you can expand this v of capital X into some series. And since x, the position operator is also Hermitian, what will happen, this will act on the bra, and it will bring out a small x. That means, the equation that we saw, it will also serve as this, since x is an Hermitian operator. And I'll give you guys some, the type in the type exercise, you will also figure out why this is Hermitian. So using that, I can write it like this. And here for P, I directly use the representation. Like P is something that generates the space translation. So if I write this whole equation in a proper way, this will be negative I squared. So you still get a negative sign. H bar squared to M P squared psi E of x dx squared E of x psi E of x equals to E of psi E of x. Now this is a differential equation, a second order. It may be linear, it might become non-linear depending on V of x. But now you have something to work with. You can plug in potentials, plug in boundary conditions, and you can solve for the energy eigenvalue over here. And for the energy basis wave function, the position basis wave function as well. So, sorry, what was I calling this? I think I was calling this the energy basis. Sorry, the energy basis wave function, my bad. The energy basis wave function. So these are two quantities of interest that you can solve for from this differential equation, depending on the value of v of x. Now, what about this time-dependent part? You can do the same thing over here as well. You can go for the position basis representation. You can go for the momentum basis representation or the energy basis. It's up to you. And since the formal solution goes like this, and we have some Hamiltonian, H. So maybe we can try for the energy basis. We can project this equation, the master equation, into the energy basis. That will make our life easier because Hamiltonian is a Hermitian operator. How will that work? Well, we can do this energy. Oops, I think I was calling it like this. And then I have this. I'm just sandwiching. Sometimes it's referred as sandwiching, or I'm taking the inner product of this thing. Since these are energy bases, I have IHT. Then you have psi of, oops, sorry, psi of 0. So this becomes, let's call it capital psi. How do you write capital psi? Like this. Yep. What's the notation I used? For here, I called it psi here. It's okay. I'm using really bad notations over here. Okay, let's just write it like this because you're gonna get something out of there as well. You have negative I ET and you have 0. Why? Because you can write this negative IHT as a series 1 minus IHT, then plus negative IHT squared, which means multiply H twice, 2 factorial, and so on. And all of these things will act on this energy basis, will give the energy eigenvalue, and you can show that this will become this. So the idea is if you can solve this equation, the time independent one, I'm not using this ease anymore. If you can solve this one, then you can use that answer and put a time evolution operator. This is known as a time evolution operator. Operator to know the wave function at a certain time t. And there's another note. This time evolution operator is something called an unitary operator. Unitary operators are such that, let's say, if you have an unitary operator which is given by u, which is, let's say u is a unitary operation, then u dagger u is equals to identity. This is an example of this unitary operation, e over negative IHT. This is something unitary. In fact, you can, if I'm not wrong, if I recall correctly, if you have e over IAT, where A is Hermitian, this structure always gives you an unitary operator. You can try to prove this if you want to. It'll be a nice matrix exercise like that. Linear algebra exercise or matrix. Like you can select a specific matrix, let's say 2 by 2, 3 by 3, and so on, or you can even do it for the most general case. So I think I'm almost there. Now, before I give a break and take the questions, is there anything else that I need to cover? Let's see. Oh, the probability and the expansion with basis. Yep, I haven't covered the probability amplitude. So now that we talked about some wave functions or wave vectors, we want to talk about probability. So we're gonna define probability a bit different here. um, what we're gonna do is that, let's say we have some state. From now on, we're calling them states, the state of a particle. And what we will do, we'll write them in a linear with a how do I say this? As the linear combination, like this, at a certain basis. So this is your basis. This is the whole thing, the state. And you already know this is known as a linear superposition. You know, if you're only considering linear algebra, but in quantum mechanics, sometimes people even call it quantum superposition. So what does this mean? Well, it means that thing, you have a cat. I don't know how to draw a cat, but I guess, yeah, this is a cat. Let's say it's like the state of the cat is some probability A with state being dead, like inside the box with some radioactive tube light or something. I don't know. That's gonna spill out all the radiation, the Schrodinger cat. And B is some number, and this state is alive. This is a linear combination, and so is this over here. So when we talk about these basis things, these can be physical states. For example, spin up, spin down. Um, what else? It can represent the first energy level, the second energy level, and so on. And the coefficients that we have over here, they represent the square root of the probabilities, roughly speaking. So how do we define the probability? Well, let's take the example of this cat. We want to find out what is the probability after we open the box, we find the cat dead, we find a dead cat, that is. It's like, we're projecting into the dead space or the dead basis vector. And if you do that, I know, since I'm calling them bases, you should know they are all orthogonal to each other, or orthonormal to each other if you consider them normalized. But since they're bases, they have to be normalized. Normalizing means, making the norm or the length of the whole thing one. So dead with cat is just A, right? And then A can be a complex number in general, and complex number as a probability doesn't make any sense. So for now, we'll take a mod squared. Even if it's a real number, we have to take the mod squared. And this is known as the probability. So the coefficients are in this sense, the coefficients are the square root of the probability. So let's say I write down a state. No, let's write down the cat state. Then we will deal with other state. So let's say the cat is how do I say this? A, dead. This is alive, and this is DA. D stands for dancing. You get a dancing cat. I don't know. And what else? You get a standing cat. ST. So what are the probabilities? Well, probability of being dead is mod A squared. Probability of being alive, okay, so dancing cat, let's assume this is not the same thing as alive. So by alive, I mean a sane cat, like doing a meow meow instead of dancing. If a cat starts to dance, that's not the same cat. So yeah, this means same cat. And this is a dead cat. This will be mod of B squared. The probability of getting a dancing cat is mod of C squared. And the probability of getting a standing cat, standing on its toes, looking out of the window or something, is D squared. And They are all real numbers when you take the mod square, because A, B, C, D, they can be in general complex, but when you take a mod square, you get something real. And since we are calling them probabilities, mod A square, mod B square, C square, D square equals to 1. You can also justify it by using the completeness of a basis. Since I uttered this word, I should just at least give you some idea of basis. It really means if you add up all the bases, they give you an identity matrix. This is something called an outer product. Is this an outer product or an exterior product? If I recall correctly, yeah, people call it outer product. Yep. All right, but yeah, don't worry too much about these things. The takeaway is sum of all the oops. The takeaway is the sum of all the probabilities is 1. It has to be 1, otherwise it doesn't make any sense. So sum of all the probabilities is equals to 1, which means if you have a state written like this, then which really corresponds to this fact. I mean, you have to choose a normalization factor. Sorry, I didn't introduce that, so let's skip that. Let's not complicate this whole thing. Yeah, so this is all about probabilities. Okay, so what have we covered so far? Let's see. We covered about some basic notations, gave some definitions, what are states, the Schrodinger equation, the time-dependent and the time-independent form, like that's just writing things in two different bases. Yeah, I think I covered pretty much everything I wanted to. So now I think I can take at least 5 or 10 minutes to take questions, discussions. Absolute space. I never heard of the term. So Rakan, I think I should continue with the second half, right? I think I answered most of the questions. Yeah, so we'll start the second half. And the second half of the lecture, we are going to work work with a very specific example. That is the harmonic oscillator. Simple harmonic oscillator. So from now on, let's work explicitly in the position basis. And since we want to deal with the harmonic oscillator, we know what the potential is, right? This is 1/2 m omega square x square, where omega is square root over k by m. I mean, we don't need the k by m. It's just showing like, there is some sort of frequency to that oscillator. And you have the psi, which is again a function of x, but I'm not going to write it explicitly, with e of psi. And our goal is to find this psi and e. And if you are someone who loves to deal with differential equations, solving them with special functions, you will find the answer in terms of harmonic polynomials. I'm not a big fan of solving them in this way, so because I'm not really good with dealing with special functions. So let me just give you the answer, and I'll just put a small index in, and this will be apparent in a few moments, like why I'm doing this. So this wave function for this simple harmonic oscillator looks something like this, if I'm not making any mistake. By mistake, I mean some factors, numbers and stuff. By exp means e exponential m omega x square to h bar. And then you have this h of n thingy, m omega h bar square root x. This is something that's been known as the Harmite polynomial of nth order. How do you get to the solution? Just try a series solution of differential equations, look for recursion relations, and then you'll realize, oh, this is another special function known as the Harmite polynomials and stuff. Every book on quantum mechanics will have the complete derivation of this, so there is no reason for us to do it, to be honest. And the energy eigenvalues will look something like this: n plus half h bar omega, where n equals to 0, 1, 2, 3, dot, 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 dot. N equals to 0 corresponds to the ground state, the state with the lowest energy. So this is what Schrodinger equation does to you. You have the harmonic oscillator potential, but now you'll see that energy is not continuous anymore, rather it's discrete. That is, you take this differential equation, you apply the boundary conditions, and this is what you will end up with. And you can even try the most simple thing, the infinite well potential. The setup is something like this. Here you have zero potential, here you have infinity potential, and the boundary conditions are here the wave function psi is 0 and psi prime is 0 as well. Try to solve this, you will see these energies are proportional to n square, where n is again 0, 1, 2, and so on. Okay, so this is not again, this should be fairly easy to solve. You can try to do it by your own, apply the boundary conditions, and you'll see the energies will be proportional to n square. And if you have this length, I think it was 1 upon L, but whatever, that's none of our concern. We just want to show that this is discrete. So this is what Schrodinger equation does, like energy is discrete. But compare this with the classical counterpart, where this was 1/2 of k capital A squared, where you called A the amplitude, k as the spring constant, and so on. You can write it in a few different ways. So here energy was a continuous thingy, but when you deal with Schrodinger equation or quantum mechanics, energy is discrete. Fine, this sums up everything, but why I'm putting so much importance in simple harmonic oscillator? Let me give you some motivation. Let's say you have one oscillator like this. Oops. This is one of the oscillators, the same one. Now what you do, you put in another oscillator. Then you put in another oscillator and so on. So at every point, think of these grids as your space. And imagine every point possible. At every point, you put a simple harmonic oscillator. That will give rise to many particle states, which will force you to do a quantum field theory. That means you are doing some sort of a quantum mechanics, then you put in special relativity n, that will give rise to many particle states. Quantum mechanics cannot deal with many particle states. Please do not confuse this with the direct product or the product solutions. Many particle state is another thing. So once you have that many particle thing, you are essentially doing a field theory, which is known as quantum field theory. That's pretty much the summary of it. And the tools you'll see over there, you'll also see over here when we deal with the simple harmonic oscillator. Even though we have the results, from differential equations in quantum field theory, you won't be solving any differential equations. There you'll be doing something else. But then again, I don't want to spoil everything. So the main goal for now is to understand how this solution, especially the one with the energy eigenvalue, comes from. And later on, we'll see how we can find this guy as well. But before that, I think someone mentioned about the inner product in infinite dimension. So let's just take a detour. So inner product, discrete is just like this. If you have you are working with some discrete or finite stuff, you'll have a row and a column multiplication, something like this. For example, if you're dealing with spin half or spin one, this will be finite row vector or column vectors. But what if you are dealing with continuous? That means you're dealing in infinite dimensional Hilbert space or something. Yeah. How do you write this phi and psi? I'm just going to give you the answer. Let's say you want to see them in position basis. Phi of x, phi of x. And this really comes from the fact that, the basis, I forgot the formal term for it. The basis is complete. Yeah, the completeness thing. Uh, since you are working on it. Yep. So what really happens is you just think of the identity operation like this, and then you break this identity into the bras and kets. This bracket notation has another advantage. It's a very elegant way of doing linear algebra, but since we are not doing anything with that, I'm not showing you a lot of stuff. But if you want to learn it, again, Shankar is a great reference. I'm a big fan of that book, so I'll just keep mentioning it over and over again. But you can also go for Sakurai if you want grade level. And Sakurai has some really nice problems. And Shankar gives you the mathematical, like a little bit of rigor. I think the rigor is good enough. I mean, it was enough for me. And the physical intuition as well. And Griffith is something very nice to read. Don't recommend it for graduate life, but yeah, for undergraduate, it should be fine. All right, so yeah, this is what inner product is. And before I move on to the whole harmonic oscillator thingy, I told you guys something about operators being Hermitian and non-Hermitian, right? Like how I mentioned, this is an anti-Hermitian operator. So how do we define or figure out those things? Well, let's say you have an operator like this L. If this is true, if this thing is true, then usually they are called self-adjoint. I think the most general definition is self-adjoint. Um, in self-adjoint, you do have some boundary conditions, so you get some extra terms, if I recall correctly. But since we're doing quantum mechanics, let's forget that definition. If something satisfies this will be known as a Hermitian operator. Rakin, am I right? The self-adjoint thing, with the self-adjoint thing. Can you comment on that? Hello? Can everyone hear me? Okay, wait, am I muted? Oh no. Oh, there is a Q&A. You made, oh, okay. This is not, you guys can hear me, right? Okay, 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 fine. Maybe some connection problem from his end. Yeah. So how do we write this? Well, if you're working in a basis, bring out all your favorite identity operations, dx prime, dx. Let's see if I'm making a mistake. X prime, L, X, X, Y. And these are some fun to do stuff. Yeah. Again, yeah. So yeah, we're not gonna use any of this. Just because someone asked, I thought it would be fair to just give them some definitions. And this will now be psi of x prime. This will be some, well, I didn't show you how to represent operators, but this is some general operator. How do I write this down? It's on the position basis thing, so let's write it like x prime. It's a general operator. We don't know what this is. If it's a momentum thing, it will be some ddx, and the x prime will go away because there is another delta function. And again, we don't need any of those, so I didn't mention any of those. And this is 6. And this is the double integral you have. But it should go away because there should be another delta x minus x prime. And in case you don't know what a delta function is, a delta function is something that is defined by this. Um, from where to where? Okay, let's see. I don't know, minus infinity, plus infinity, 1, whatever. It's like a peak, like this, impulse. But we don't need any of this to do the stuff that we're gonna do. So I never bothered mentioning about it. But you're gonna see it in the QFT preliminaries as well. In fact, this will be your best tool when you deal with QFT. You're gonna love the delta function. Like, let's say you have some function, some trial function, you know, there's this delta function, prime, prime, prime. This is just, let's say from A to B, such that this x prime is in between a b, so this will be just this. You're gonna love it. Yeah, so this was an aside, so not something that's pretty relevant to us for now. This was an aside. Yeah, I take a lot of detours. Yeah, I get distracted pretty easily. Okay, so what do we want to do? We want to study the simple harmonic oscillator, and our primary goal is to get the energy eigenvalues. We already know what this is, but we want to derive it in a different way. So let's start with the Hamiltonian first. The Hamiltonian for the oscillator will be 1/2 of m omega squared x squared. Now I'm gonna do something pretty mysterious. If you already know it, good. If you don't know it, you're gonna find it very weird. But trust me, bear with me, everything's gonna work out fine. So from Shonkar's book, I got to know like this is a method that Dirac used, Paul Dirac. People call it the method of factorization. The idea is to get a, um, you know, it's just to diagonalize the Hamiltonian, so you know what the eigenvalues are. For example, instead of this complicated infinite dimensional thing, let's say your Hamiltonian is just a matrix. Let's call this H prime. Let's call this 5, 6, 7, 8. If you want to know the eigenvalues, I mean, let's say this is a Hamiltonian, some sort of. Very weird, but some sort of. Let's say you want to know the eigenvalues, right? What do? You just find H prime in a basis where all the elements are diagonal. That means you want to diagonalize the Hamiltonian. So that's the idea. So what we want to do, instead of writing things in terms of P and X, we want to write them in terms of new variables so that the Hamiltonian is diagonal. If you're interested, you can look into something called a Bogoliubov transformations. And it's the same thing as well. In quantum mechanics book, since people see it for the first time, people usually call it the factorization method. All right, so with that in mind, our goal is to diagonalize the Hamiltonian. To that end, we define some new operators, and there will be a linear combination of this x and p. Let's define a, m omega. I'm using the convention from Shankar's book. I think different book uses different conventions, but I decided to stick with the Shankar one. But the end result is gonna be the same, so it doesn't really matter, to be honest. And similarly, you can define the conjugate of this with the dagger symbol. 2h bar 1/2 x minus I 1/2. Oops, there's a 1/2. 2m omega h bar 1/2 p. Now, we already mentioned in the very beginning, x and p is I h bar. And there's an identity operation, but from now on, we are lazy. We are not going to write the identity. It's just understood. If you don't write anything, there's an identity, like a identity matrix and stuff. So with the help of this, given this is true, an exercise for you people is to show that a dagger, the commutator is the identity. Yeah, this is an exercise. Please do it when you are free or when you have time. If you have done it, great. If you haven't done it and seeing it for the first time, do it. Okay. So once you have that, well, why we're doing all of this, just bear with me for now, and then everything will be crystal clear. So with that in hand, now let's try to write the Hamiltonian in terms of these new variables, a and a dagger. If we do that, it will become h bar omega, a dagger a, plus 1/2. If I'm not wrong. So this looks pretty nice. Why? Because let's say we have the A and A daggers, let's say we know what A's are. Again, these A's are operators as well. And as you can possibly see from these two equations, this A and A dagger, they are not Hermitian. However, A dagger A, this is Hermitian. Because A dagger is just A dagger A. Transpose, complex conjugate, you get the Hermitian thing. So, okay, in case you don't understand how this is happening, well, let's say you have some operators A, B, C, you want to dagger them. This looks like C dagger, B dagger, A dagger, okay? It's like you dagger them in a reverse manner, like, starting from the right to left and stuff like that. So this is pretty nice. This is pretty clean. And if I want to find the eigenvalues of this H, what do I gonna do? I can take the energy eigenbasis. I think someone suggested to use the energy basis like this. So I'm gonna use it like that. And we're gonna introduce the expectation value very soon. That you were wondering, okay, why am I not talking about expectation values, but I'm gonna talk about it now. So we want to find the energy eigenvalues. So for this particular state, let's say the energy eigenvalue is E. Again, these notations are at first, if you're seeing it for the first time, it might be very confusing, but once you get used to it, yeah, it's gonna feel more natural. So we want to find this number or the energy, right? So what we can do, we can try to sandwich this. Since these are basis vectors, orthonormal, this is 1. So the value of energy is something that looks like this. There's a bra, there's a cat, there's an operator in between, right? This is a structure of a expectation value. Or so-called the average value. So if I now put the new expression for the Hamiltonian, the E or the energy eigenvalue looks something like this. A dagger A plus 1/2 E, and h bar omega is just numbers, these are numbers, so they come out of the whole thing. So this is h bar omega E, A dagger A, E, E. But since these are basis vectors, this is again 1 h bar omega. Sometimes people even write the expectation values like this, they get rid of the basis And you can just write the basis downstairs as well. It's up to you. And this is this. So this is the energy eigenvalue, right? So it all comes to computing this quantity. That's very nice. We don't have to solve a very complicated differential equation. So how can we do this? To do this, we just need to know how A acts on E. That's all we need to know. Because if I can find how A acts on E, first it gives me something mysterious. Then I can figure out how A dagger acts on E by taking the Hermitian conjugate. So this is the goal now. We want to know how A acts on E. So I'll show a small computation and we'll try to justify it, like why I'm doing this. So we already know the energy eigenbasis. Like in the energy eigenbasis, the Hamiltonian is just the operator that gives the energy eigenvalue up for the energy and stuff like that. So you already know this thing. So let's use this thing to our advantage. For that, you need to compute the commutator first. Okay, you know what? Let me just use it later so that it's evident to you why I made it. So we want to figure out this action of A operator to the energy eigenbasis, right? To that end, let's do this because we only have two operators, the Hamiltonian itself and A, and the basis is E. So the most general thing we can do, we can take a product like this and see what happens to it, what happens to its rate. So instead of HA, only if I could push this H to just next to E, I could bring out the eigenvalue, right? So to that end, what I do is I do add and subtract AH like this. And what happens over here is the commutator of H and A with E. That's what is there. And oops, there should be a bracket. And then I have A, E with the vector E, right? So it turns out now somehow I need to figure out what is the H commutator with A. What is H of H commutator? How do I say this? H commutator A. This is another exercise. You should do it using the fact that H can be written as H bar omega. Can I do one thing? Can I just take H bar to 1? Okay, you know what? Let me do it in another way. Let me just rescale the Hamiltonian. I think that would be much better. Okay, let's not change anything. Let's just do it the old-fashioned way. Yeah, because switching notation is so much will confuse people. Okay, so we want to compute the commutator like this. So this is an exercise. You should do it, and this should give you, let's see, just A, right? There was not a minus sign. Yep, this should just give you an A. But do you have a H bar omega in front? That's the question. Am I missing something? Yeah, I'm just not sure about if there's a factor of this. Okay, you know what? Let's just do it. Let's do it from scratch. Let's not assume anything. So instead of H, you have H bar omega, A dagger A plus 1/2 with A. You have H bar omega. Okay, that's cool. You don't need this. This is a number. This is an operator. There's an identity operation, so the commutator is 0. So finally, what you have is A dagger A with A And if you expand this out, use the identity A dagger A equals to 1, you should get H bar omega A. Okay, so there's a H bar omega in front. I might be wrong. I mean, usually I work in omega 1 H1 basis, but yeah, it's just rescaling the Hamiltonian, which really means you are measuring energy in terms in the scale of frequency. But okay, it's fine. So if you do this, the essential idea is like H bar comma A. I mean, HA is proportional to, maybe there's some factor, I don't know. So if we do it and we keep it like this, this energy thing, okay, so this is H omega. I should have just rescaled everything. A, okay. It should give me -1. Okay, am I missing a sign somewhere? Let me see. H. Yeah, I'm missing a sign. It shouldn't be A, it should be -A. Let me check my notes. The notes I made. Sorry about this. Yeah, I think I'm missing a minus sign somewhere. There's a handwritten note, so yeah, I can see it. Okay, I'm not missing a sign. Okay, then why am I not getting a minus sign over here? Negative AH. That's H commutator A. Okay, that's okay. And then what did I do wrong? H of A of H. This is H A. Commutator, we have AH with E, the energy eigenvalue. Oh, I made another mistake. There should be a H bar omega in front because H was something like H bar omega and the whole thing. So yeah, there should be H bar omega. Okay, so this is correct. Why am I getting a plus sign? Sorry about this. Okay, I can bring up a minus sign, but that's more like cheating. Using the idea that this is negative. Okay, I didn't write this in my note. Why should I do it like this? Because you can also bring up a plus sign as well for the A. Oh, in that case, the definition of A would change. You would call A as the creation operator and A dagger as the annihilation operator. Okay. Okay, you can do it both ways. Fine. Okay, so let's write it. Let's follow the tradition where we call A as the annihilation operation. So AE, E. This is again native A. Okay, now vector E. A of E vector. This is like E -1 A with E. Okay, so for now, let's not worry about the factors. Like imagine H cut omega equals to 1. You can always do that. I mean, if you want to. I mean, the way it will work is the following. If you, the Hamiltonian was something like this. A dagger A plus 1/2, right? So instead of this writing this h cut omega here or h bar omega here, you write h by h omega with some h prime. It's like doing some dimensionless stuff, energy is dimensionless. It's just a number because you see there's a 1/2 over here. So a dagger a will give you some number, that's it. And in that case, the energy basis instead of E, as Shankar does, you can write them as epsilon as well. So for now, kindly ignore all these factors that you have. Or you can convince yourself, okay, instead of working in the dimension full form, let's work in the dimensionless form. Dimensionless form makes your life a little bit easier because keeping track of these factors is really painful, at least for me. All right, so what do we get? What's the conclusion? H of A, E is equals to E minus 1, A of E. Now think of it like this. A of E is equals to some A prime, some sort of a linear transformation because A and A dagger are linear operators, right? They're written as a linear combination of the position and the momentum. So H acting on E prime will give you E minus 1, E prime. So let's call this E minus 1 as E prime. That means this E minus 1 is the eigenvalue of this state. That's something I'm giving by E prime. However, the definition of the Hamiltonian in the energy eigenbasis was it should spit up the energy eigenvalue only for the corresponding state. So if I compare these two equations, I mean by these two, this one comes from the above. Let's call this 1, 2, 3. So if I compare 3 and 2, I can then say a sum operation that works on this and really brings the state down by 1. That means if the state was in the state is in an energy level E, it goes down one step, sorry. And if you want to get rid of this proportional sign, you write, okay, there is some sort of a number associated with this. Let's call them C1, and this is E minus 1. At this point in time, people, since you're dealing with numbers, instead of E, you can also write some N. They mean the same thing. Like E means energy, N means energy as well, since we are scaling things like this. H by H cut omega equals to H prime. And most of the books use this in like this convention as well. So from now on, let's switch the notation again. Instead of E, just write N. So this is N minus 1. Similarly, you can show by using this expression, like starting from this thingy, that a dagger of N is equals to some C2 and plus 1. So from there, these guys, A and A dagger, have their names. The ladder operators are the creation and annihilation operators. And once you have these two operators, if you have any state N, you can use A to go down one step. So if you apply A twice, you can go down 2 steps to get to N2. You can apply it even more to get down as much as you want. However, that is not physically possible because if you are dealing with a theory that that doesn't have any bound state, that is not bounded below, it will lead to instabilities. Physically, that doesn't make any sense. So we will define some A of N0, which we'll call it, we'll call it the ground state or something, or the state with the lowest energy. And once this A acts on this N0, it will give you 0. That means it's completely destroyed. So from there on, people usually call it the annihilation operator. And after it gets destroyed, whatever you apply a dagger, you apply a, you apply a dagger over 100, it doesn't matter because it's zero. The state is no more. Think of it like, you had a particle, but somehow you destroyed it. Yeah. And however, for the creation operator or a dagger, you can go up to any state you like apply it 100 times, maybe. So you can finally go up to some n plus 100 and stuff like that. That's okay. You don't have to worry about how high you can get. So with all that in mind, the conclusion is the creation operator acts on some energy state. And I'm just going to give you the answer right now. I don't think there's much time left. Oh God, there's only 8 minutes left. Okay, but we're almost done, so that's also good. The summary is you have an annihilation operator. It works on some energy basis. It pops out that energy. I'm writing N. You can write E if you want to. You can also write this, like if you want to. And it's okay. It means the same thing. It pops out the energy for that state, then square roots it. However, now your energy level has gone down by 1 step. And the creation operator, it gives you square root over n plus 1 with n plus 1. So if you want to compute the expectation value, this will just become n. Well, how can you prove this? You can prove this just by considering this product. Just consider this product and use the fact that this is equals to this. You should be able to do it. If you cannot do it, you can look into Shankar, you can look into Sakurai. These two books, I mean, I don't remember if Sakurai has it or not, but in Shankar you have it. You have the proof how you get the n thingy, or the energy thing, which has been just rescaled by h cut omega and so on. So once you have this, so your rescaled Hamiltonian, again we recall this h prime, which is a rescaled thing, is h by h bar omega. This is just n plus 1/2, or I mean, sorry, the expectation value, so to say. So if you write with all the scalings in the theory, this is what you have. It's the same result that you can get from solving the differential equation. And if you haven't seen it, I suggest you take a look at it. But this creation and annihilation operator also helps you in terms of determining expectation values of position and momentums. Because, I told you that the energy expectation values are something like this, right? And you already found it. Pretty simple answer. What about some expectation value of the position or of the harmonic oscillator? Or maybe position squared, or maybe position cubed, or maybe position over n. If you try to do it with the Hermite polynomials, it's like living in a nightmare. But with these operators, it's like a walk in the park. Anyone can do it. So if you want to do it like this, you can do it in the energy basis, like the expectation value in the energy basis. It's not gonna matter which basis you work on. It's gonna be the same thing. So we defined A with some linear combination of X and P, right? Some X, like there were some factors, and a dagger with again some numbers, X and P. What you can do, you can use these two equations to solve for X and P in terms of A and A dagger. And if I recall correctly, this should be proportional, like X should be proportional to A minus A bar, I guess. There will be numbers like H bar, omega I, and all that other stuff. and this should be this. So then what you can do, you can use this identities. Yep, you can plug those in and compute this. Same goes for the momentum. Same goes for any quantity that, let's say, you have some weird quantity. You have some operator, p squared x cube, and you want to know the expectation value of this. This is an observable because x is Hermitian, p is Hermitian. So you want to compute the expectation or the average value of it. You can work in the energy basis to get everything you want. If you want, you can solve for x and p in terms of NA dagger and try it at home. And now since we're done with the eigenvalue thing, you might ask, okay, is there any way we can get uh, a wave function, in the energy basis back? We are dealing with this dagger A, and is there any way we can get the energy wave function back? So the answer is yes, and this one is even more insightful rather than using all those Harmonic polynomials. And again, this is adapted from Shankar's book. It's in chapter 7, if I recall correctly. At the very last section, he demonstrates this pretty beautifully. You have this representation of the ground state, let's say. Since you want to know the psi of x thingy, that is coming from you work in the energy basis first, then project it into the position basis to get the wave function. What do? You just do this. Now write A was what? A was some number. Let's call this number C1, X, C2, P. The C1 and C2s are those H bar omegas and other stuff. So I write it like this. C1X, C2P, and 0. And X, since there's a plus thing, this is a linear thing, this will be C1, some small x, negative I, H bar, dd of x. There will be a psi of x, obviously. And obviously I'll put a 0 just to indicate that this is the ground state upon which the annihilation operator acts and destroys the state at the same time. So this is a pretty simple differential equation. You can solve it. You will see there is some Gaussian state. And since once you know the ground state, you can build up the other state using the creation operator. Let's say this is the ground state in 0. The next state is just if you act a dagger on the ground state, this is the ground state energy +1 and 0 +1. So what do? Well, you just find out the solution for psi 0 of x. You find out the position representation of a dagger, and yeah, you just this is a representation in the position space. Let's say I denote this with R of a dagger. Psi 0 of x, it should give you psi 1 of x, and so on. In fact, for any state n, it can be built up from the ground state like this. And this is very simple to prove. If you do a dagger 0, this is just 1. If you do a dagger square with 0, this really means a dagger 1, which is 2, 2, and so on. You do this n times, you get this. So essentially what you're doing to find the psi of n or the nth eigenstate is just taking the position representation of this equation. And yeah, what you're gonna see in quantum field theory is you're gonna start with some Lagrangian that is very similar to the Lagrangian of simple harmonic oscillator. The only difference is in quantum mechanics, you had one oscillator. There, not only you'll have oscillator at every point in space, but it's a space-time itself. So their time is not a parameter anymore. Yeah. And that's pretty much it about the simple harmonic oscillator. You're gonna see again this A and A daggers, creation and annihilation operators. And another way of introducing them is to, when you write down the Hamiltonian, p square, let's just write this as p square, x square, something like this. You can factorize it. This is one way of writing it. And the other way is to just how do I say this? Write them in terms of a Fourier transformation. That's something I'm not going to show you. I think in the prelude classes, like the introductory classes, you're gonna see a lot of Fourier transformations. In fact, when earlier I mentioned like the momentum operator in the position basis looks something like this, and forget about h, whatever, doesn't matter. If you take the Fourier transformation of this guy, you will get just p. So when you switch from one basis to the dual basis, you have to use a Fourier transform. That's what it does. Even the identities, let's say in the position basis, it looks something like this. In the momentum basis, you're going to have a 2 pi dp p p. It's pretty simple. You just write the Fourier transformation or do a Fourier transformation of x using this. You get rid of all of x, and what you have is a p of something. And I think someone asked this question, like, why is p of x is some e over ipx or something. Maybe I'm missing a minus sign. You can do this, you can prove this from a Fourier transformation. Or you can also try to do it from the Schrodinger equation, like the time-dependent one. But this is essentially a result of Fourier transformation. So all of these things are not, I know when you see it for the first time, it seems very odd, but if you study by yourself, you can find out the connections. And again, 2 hours is not enough because the formality, the formal structure, it's pretty big. And I just tried my best to pour information down on you guys. And yep. Okay, so this is pretty much it. So just before I finish talking, yeah, I'll just take 5 more minutes. I'm gonna, the Schrodinger equation is pretty nice, right? I'm just gonna give you guys an exercise. You know what? I'm not gonna do it. I'll rather give you an exercise. This is the Hamiltonian operator, so this is the energy operator. What happens if I do some relativistic stuff? In relativity, this is p squared m squared. Okay, I'm not gonna write c. Yeah, c is equals to 1. C equals to 1. This is the God-given unit. H bar, C bar, I don't know, K, even sometimes G. Yeah, whatever. For now, H bar and C bar, they're 1. So this is gone as well. So what if the Hamiltonian is something like this? Energy squared is p squared plus m squared. But so if I write this in an operator notation, taking only the positive square root, since we are doing operator stuff, we are being careful. This is capital P square. And again, mass is a scalar, so let's just write m square. And there's identity operation over here, square root. So ddt psi p square m square square root. you know, it's just me being me. I know a Hamiltonian. I want to put everything in Schrodinger equation and quantize everything. Maybe I'll even write a gravitational Hamiltonian, like, potential energy, kinetic energy, put everything into this quantum equation and maybe quantize gravity. I'm very ambitious. Yeah. So yeah, this is something I want to try out. So what do you think will happen if I go to the position basis? That means I want to write this simple thing, the simple differential equation. E of silence. What do you think will happen? This is something I want to leave as a food for thought. And if you are interested, you can try to do it. And you'll also find it in any quantum mechanics books, I guess. In Shankar, it's the very last, the second last chapter. The chapter is called Dirac equation. So from here on, you can do a Taylor expansion, work in the non-relativistic limit, or work in the first order of relativistic limit, and then you're gonna get a Klein-Gordon equation. The very first thing you're gonna see in quantum field theory, which really looks the same, but instead of putting an oscillator in one point, you now have one single oscillator at each and every point in space and time. So that gives rise to multi-particle states. And there is another thing about the Schrodinger equation is that, in relativity, we want to treat space and time on equal footing, right? But if you look at the Schrodinger equation, especially the position representation, this equation is second order in space because you have this from the kinetic part, you have this second derivative with respect to x. However, you have only the first derivative with respect to time. So it doesn't, it doesn't treat time and space on an equal footing. So what Dirac wanted to do is instead of taking the square root, Dirac wanted to make it a whole square type of thing. Like write this p square plus m square in such a way, this operator p square plus m square in such a way so that this will become some alpha plus beta. Again, this might be some operators whole square, or maybe there are even more stuff. The idea was to get rid of the square root. So that's the Dirac equation. You're gonna see it in quantum field theory, so I'll not spoil you anymore. But yeah, if you want a pedagogical derivation of Dirac equation, you can see Shankar, or maybe in Sakurai has two books on quantum mechanics. One is the red one. I think it's just Introduction to Quantum Mechanics, and the other one is Advanced Quantum Mechanics. I think the Advanced Quantum Mechanics one talks about the Dirac equation. All right, with that in mind, again, 2 hours is never enough. I tend to talk a lot, so yeah. But this is pretty much it. With these tools, you should be good. I mean, I'm not saying you should be good, but it should make your life a little bit easier when the quantum field theory thing actually starts. The main thing is you have to know the creation and annihilation operator, and that's it. You do everything in terms of them. But in quantum field theory, you're gonna be more interested in finding what's that called? The endpoint functions.